All right, we are working on the lecture on the introduction of trigonometric functions based on right triangles. The first page looks like this, and we're now ready to move on to pages 2 and 3. Now, page 2 has a bit of text for you to read. I don't know that it's that helpful for me to read it to you, but let me just point out what we're going to be working on here, and then I'll flip the page and we'll get started. If you look at the unit circle, that means the circle with center at the origin at point 0, 0, and with radius 1, if you wrap that around, this will contain, of course, infinitely many points. And what we'd like to ask is this question: if we were to slice a ray out through here so that this angle is 30 degrees or 45 degrees or 60 degrees or 90 degrees, and of course we have 0 degrees here, could we tell exactly these points of intersection between this ray and the circle? And it's going to turn out that that is a calculation that's really helpful to do. It's going to reveal something about the trigonometric functions to us. Now, the other thing I want to just mention that's on this page is the strategy we're going to use to do that. And that is, let's suppose we took, say, this 30-degree angle here. If you look at it in just the right way, you can see that there's a right triangle hidden in here. We follow the x-axis until we get just right under this point of intersection. We go straight up, hit the point where the 30-degree ray intersects the circle, and that defines a triangle for us. And we can use the properties of the 30, 60, 90 right triangle in order to compute the coordinates of this point. The x-coordinate is the length of this side, the y-coordinate is the length of this side. And we're going to find out that those are root 3 over 2.5. And that's what we're really going to look at on this page to do in detail. Now, I have drawn a very much larger picture here so that we can see what's going on a little bit. So what we're thinking of right now is we have the case of 30 degrees, and we are going to draw a line that's perpendicular to the x-axis and cuts through that point of intersection between the 30-degree ray and the circumference of this circle. Now, remember, this is a circle of radius 1. So x is 0 here. We move over then 1 unit. We already know this point of intersection. That x-coordinate is 1 and the y-coordinate is 0. And in the same way, up here at the top, this is when you swing the ray all the way around, you're right directly over the origin. Well, of course, the x-coordinate is 0 then, and the y-coordinate is 1, because this is the radius of the circle, and the radius of the circle is 1. Okay, let's see if we can compute this point right here. Well, this is a 30-degree angle. This is a 90-degree angle. These have to add up to be 180. So we have used 90 plus 30. That's 120. It leaves 60 left over. And how lucky, we're looking at a 30, 60, 90 right triangle. Well, we have the theorem about 30, 60, 90 right triangles. It tells us this, that in any 30, 60, 90 right triangle, the side opposite the 30-degree angle is just 1/2 the length of the hypotenuse. But our hypotenuse, well, that's the radius of the circle, right? And the radius of this circle is 1. So that side is 1. And then we know from past work that that's the square root of 3 over 2. And it's very easy to check. It should be the case that this squared plus this squared is equal to that squared. Root 3 over 2 squared plus 1/2 squared is, well, square root of 3 squared is 3. 2 squared is 4. 1 squared is 1, 2 squared is 4, 3/4 and 1/4 is what we have is 1, and that also, of course, is equal to 1 squared. So it is true. This squared plus this squared is equal to 1. That's a good confirmation that we have this correct. So this distance along here is √3/2, but of course, that's also the x-axis, the x-coordinate of that point right there. √3/2. And this distance along here, well, we've just computed it. That is 1/2, but that's also the y-coordinate of this point. So this is 1/2. Okay, how about if we do this one right here? Well, same thing again. We would simply drop a perpendicular from the x-axis up to that point. This is now a right angle. We have a right triangle here. This angle here is 45. And it's going to be easier to do this if we make a little sketch down here. So now, this is 45 degrees. That makes this 45 degrees because the sum has to be 180. 90 plus another 90 is 180. Half of 90 is 45. And if the radius, if this hypotenuse is 1, and it is because the radius of our circle is 1, then we know that we are working with this triangle here. It's one of those special triangles that we said we need to get in our list to memorize. And again, you can check that very easily. The square of 1/√2 is 1/2. So 1/2 plus 1/2 is in fact 1, and that's 1 squared. So this satisfies the check with the Pythagorean theorem. And in the same way, then, we can go here and say, okay, so this distance right along here is 1/√2. That's the x-coordinate. And the y-coordinate, well, that length is the same as that when the angle is 45. So that's 1/√2. And we have just one more that we want to look at, and then we're gonna make some conclusions. Sweep up here now 60 degrees. Well, one more time, in order to do that calculation, we would drop a perpendicular here from the point down to the x-axis. And now things are just really kind of reversed from where we had them on this triangle. We're now looking at a triangle that looks more like this. This comes up at a 60-degree angle. This is the perpendicular to the x-axis. That's a right angle. This is 60. 60 plus 90 is 150. We need 30 more. So we do once again have a 30, 60, 90 right triangle. We just aren't used to seeing it drawn this way. Well, the theorem says that the shorter side, the side opposite 30-degree angle, is 1/2 the length of the hypotenuse. But one more time, that hypotenuse is just the radius of our circle, which is 1. So this is 1/2, and this is √3/2. And now the x-coordinate is 1/2, and the y-coordinate is √3/2. Okay, now let's just do some quick observations here. Let's go back to this one right here with a 30-degree angle. Now we have another calculation we could do. From this picture, we could say, well, what is the sine of theta, where theta is that angle? Well, now we actually know that's a 30-degree that we're working on, 30-degree angle. And the sine of 30 degrees is opposite over the hypotenuse. Well, the hypotenuse is 1, so this is just 1/2. The sine of 45 degrees, well, that would be from this one, this picture here, right? Opposite over hypotenuse, that's 1/√2. And the sine of 60 degrees is, well, that comes from the last one we did, 60 degrees, opposite over hypotenuse, root 3 over 2. So what we're getting here, 1/2, 1 over root 2, root 3 over 2, notice those are occurring right here with the 30 degrees, 1/2, 1 over root 2, root 3 over 2. These y coordinates here, those are the sines of the angle here. So this is the sine of 30 degrees. This is the sine of 45 degrees. And this last one, this last y coordinate, is the sine of 60 degrees. Now, what about those x-coordinates? Well, same deal. X-coordinate, we, in order to get that here, it's the adjacent divided by the hypotenuse. So the cosine of 30 degrees, cosine of 30 degrees is the adjacent over the hypotenuse, is root 3 over 2, which happens to just be the very same value as the sine of 60. The cosine of 45 degrees, well, adjacent over hypotenuse, that's 1 over root 2. And check that out, that's the same as the sine of 45 degrees. And the cosine of 60 degrees, down here, adjacent over hypotenuse, that's 1/2. And that happens to be the same as the sine of 30. So here we've got cosine of 30. Here we've got cosine of 45 degrees, and this x-coordinate is the cosine of 60 degrees. Now, what you're probably already recognizing is that when I have a unit circle, and I don't draw the best approximations of circles, but I guess we can live with it. If you pick any ray here and let this angle be theta, then it turns out that the x-coordinate of this point is the cosine of theta, and the y-coordinate of this point is the sine of theta. And so when we found these points of intersection here, we were actually finding the cosine and sine values for these different angles. Now, one other thing you might notice is we can infer that this is the 0.10 and this is the 0.01 just from basic geometry. So it must be that the cosine of 0 degrees is equal to 1, and it must be that the sine of 0 degrees is equal to 0. And in the same way, if we look up here at the top of our figure, the cosine of 90 degrees must be equal to 0, and the sine of 90 degrees must be equal to 1. So we have computed a lot of sines and cosines. We've got them sitting right here now. The last thing I want you to notice is this. Let's take this. Let's take these sines. So those are the y-coordinates, and read them as we move up. 0, 1/2, 1 over root 2, root 3 over 2, and 1. Now let's read the cosines in the opposite direction. 0, 1/2, 1 over root 2, root 3 over 2, and 1, those are exactly the same thing, right? And that is what I wanted you to see. The reason I laid these out as I did, that you can see that the sine of 60 is the cosine of 30. Well, why is that? Well, it's because let's take this triangle that we used for our 30-degree angle. The sine of 30 is 1/2. It's this over this. The cosine is root 3 over 2, but if I looked at this angle, this 60-degree angle, then the sine of 30 is 1/2, and the cosine of 60 is 1/2. That's where this comes from in the names cosine, cosecant, and cotangent. It means the complementary angle. It is 90 degrees minus the angle. So in other words, if you take the sine of 30, you'll get the same as the cosine of its complementary angle, 60. If you take the sine of 45, you get the same thing as if you took the cosine of its complementary angle, which happens also to be 45. And likewise, if you take the sine of 60, you'll get the same thing as if you took the cosine of its complementary angle, 30. So that's what the means. It means switching to the complementary angle would give you this result with this pattern here. So we learned quite a bit, actually, how to find the sine and cosine of all the reference angles, 0, 30, 45, 60, and 90. And we have found out that if you read the y-coordinates in one direction, and then you read the x-coordinates in the other direction, you'll get exactly the same list of values. And that turns out to be pretty helpful.